Hey, I'm Justin from Alchitry, and in this video we're going to dive into transmission line impedance. This video was made in partnership with Altium, and in the next video we'll take a look at how the physics explored in this video relates to PCB design. So subscribe if that sounds interesting. Before we get too deep into it, we need to talk about what exactly transmission line impedance means. A transmission line is really just a pair of wires carrying a signal. It can be a trace and a ground plane on a PCB, or it can be a pair of wires in a cable. Impedance, on the other hand, is a bit more complicated. The term impedance is used to describe the relationship between the voltage applied and the current going into a circuit. This may sound familiar if you've heard of Ohm's law. Ohm's law is typically written as V equals IR, where R is the resistance. However, a more generalized definition is V equals IZ, where Z is the impedance. Impedance is a complex number, but the real portion of it is resistance. The imaginary part of impedance captures the effects of devices that store energy like inductors and capacitors. How all the math for this shakes out could be its own video series. And for the purpose of this video, we will be dealing with just real impedances, which act just like resistors. The general form for characteristic impedance of a transmission line is given by this equation. The values R, G, L, and C are the resistance, conductance, inductance, and capacitance respectively of the line in terms of unit length. Omega is the frequency of the signal, and J is just used instead of I for the square root of -1 in electrical engineering to not be confused with current. In a perfect conductor with perfect insulation, R and G are 0, and the whole thing simplifies to the square root of L over C, which is strictly real. Most of the time, this is a very reasonable approximation. When the impedance of something is a real value, then it looks just like a resistor to whatever is driving it. If we had an infinitely long 50 ohm cable, it would be indistinguishable from a 50 ohm resistor to the device that's pushing signals down it. The major difference is that the energy in the cable travels down it, but the energy in a resistor dissipates as heat. Looking back at the equation, we can see that the impedance of a wire is mostly determined by its ratio of inductance to its capacitance. A transmission line's inductance and capacitance are properties of its geometry and the material between the conductors. When working with the PCB, we can choose some of the properties of materials between the copper when selecting a stack-up. The stack-up also determines how far apart the layers are. For a given stack-up, we can then figure out how wide our traces need to be to achieve the impedance we want. We'll dive into all that in the next video. For this video, I want to get into why we even care about this and what happens when we get it wrong. To take a look at this, I designed this test PCB with a bunch of different traces on it. There's a single-ended trace that has a characteristic impedance of 50 ohms, a differential trace with a characteristic impedance of 100 ohms, and 4 different differential traces with various impedance mismatches. Most of the time, we only really care what the impedance is when there's a mismatch. A perfectly uniform cable, regardless of its impedance, will allow a signal to propagate down it at the speed of light without any issues. Problems only come up when the transmission line isn't uniform or we get to one of its ends. For example, if we have a 50 ohm trace that just ends, from the point of view of the signal, it looks like the impedance jumped from 50 to near infinity. This causes a reflection. When we have a mismatch in impedance, we can calculate how much of the signal reflects back and how much continues on. This formula tells you how much of the signal is reflected given the impedance of the load ZL and the impedance of the source Z0. The voltage that continues on must be the voltage that we sent plus the reflected voltage. This is because at the boundary between the two, the voltage must be continuous. If we substitute in the reflection coefficient, we get this for the transmission coefficient. What's interesting about this is that the transmission coefficient can actually be larger than 1. If we take the case where ZL is infinite, like at the end of a wire, we can see that the transmission coefficient becomes 2. This means right at the end of a wire, the voltage doubles. How is that even possible? Well, if we think about a wave moving down the transmission line, when it comes to the end, it has nowhere to go except backwards, so it completely reflects. Right at the point where that happens, the incoming wave and the reflecting wave overlap, adding up. We can actually see this happen on our demo board. So I have one of our demo boards here hooked up with this little green wire going to an SMA connector, and that goes to our signal generator, which is generating little pulses. And those pulses are being picked up by trace 1, which is the yellow one on the oscilloscope, and trace 2, which is the red one, I have to hold over here, and we can see what happens when it hits the end. Right now, there's no termination resist or anything, so this is just the signals are going through the 50 ohm trace, hitting a brick wall, and then reflecting back. So on the oscilloscope, we can see the yellow trace. This first bump on it is the signal being sent. Then after some delay, we see another bump as it has reflected and come back. And at the end of the line, we can see right in the middle, we get a signal that is twice as tall as the signal we're sending. So in this case, we're reading about, looks like just under like 3.5 volts on the pink trace. And we're seeing that we're sending about 2 volts on the yellow trace, which is what I have the signal generator set up. It's supposed to be sending a 2 volt pulse. If I change the pulse width, right now we're at 20 nanoseconds, I can go a little bit shorter on this signal generator, but 16.3 nanoseconds is the shortest I can go. But if I make it longer, we can see the return pulse will actually then overlap with the sending pulse, and we'll get that full, almost full 4 volts, like 3.5 volts that we're seeing, summation of the pulse we're sending plus the pulse that's returning. And if I make this longer, we'll get that like very obvious stair step where we have the pulse we're sending plus the reflection, and then just the reflection. However, at the end, we're only getting the reflection, and it's all about 3.5 building up to 4 volts if we let it run long enough. The reason we're not seeing it immediately jump to that is losses in the cable and the ability for the signal generator to make a signal rise that fast. It's hard to do. And this is a medium level signal generator. All right, so now we've seen the case where the transmission line just ends. But what about when the transmission line continues, but just with a higher impedance? Wouldn't that somehow violate physics if the voltage increases? Let's take a look at an example where we have a 50 ohm line connected to a 100 ohm line. Using our formula from before, we can calculate that the reflection coefficient will be 1/3. That means the transmission coefficient must be 1 plus that, so 4/3. If the pulse was 5 volts, we would expect to see around 6.7 volts continue on past the point of discontinuity. However, that new higher voltage pulse has less power. Let's take a look at why. First, power is current times voltage. We know that the current will be the voltage divided by the impedance from Ohm's law. That tells us that the power we started with is half a watt. After the discontinuity, we only have 0.44 watts. If we calculate the power of the reflection, we get 0.06 watts. So we can see that the total amount of power is the same, even though that the voltage increased on the output. This is because the current went down due to the higher impedance. So far, we've only been looking at cases where the impedance increased, but what about when it decreases? Let's take a look at what happens when the ends of a transmission line are shorted, as we can easily demo this on the PCB. Give me a second to solder the end of this together. Using the reflection coefficient when ZL is 0, we can see that we get -1. That means we should see a signal coming back just as we sent, but completely inverted. And if we take a look at the demonstration that I've set up here, that's exactly what we see. On our board, I soldered the end of the trace to ground to give us a ZL of 0. Here we can see that the pulse we sent is, basically exactly the same, but the reflection that we see is now completely inverted. And if I change the length of these, we can see that as the pulse we're sending gets longer, the reflection also gets longer, and there's a period here in the middle where they're now interfering. So here we have the pulse we're sending, both the pulse we're sending plus the returned reflection, and then just the reflection. And the reason that this center part isn't exactly 0 is again because there's losses in the wire. So the returned pulse is a little bit shorter, a little bit lower voltage than the pulse that we sent out. So it's a little bit positive because it's not completely canceling. If this was a perfect conductor, then it would cancel exactly to 0, even though we're still sending a pulse. The two waves overlap and cancel. Typically, we don't want reflections. What we really want is a perfectly long trace that we can just keep sending data down and never have any interference coming back from reflections. Unfortunately, an infinitely long cable isn't very practical, so instead, we use termination resistors. Instead of having an infinitely long trace, we can use a standard resistor that matches the impedance of the trace. From the point of view of the signal, there is no difference between a 50 ohm trace and a 50 ohm resistor. The resistor will just absorb the energy and dissipate it as heat instead of propagating it along a wire. All right, let's now take a look at the trace with a 49.9 ohm resistor on it. The reason for this weird value is that 50 ohms isn't the standard resistor, but 49.9 ohms is. When we do this, we can see that we're getting basically no reflections. We have a little bit of a bump here. That's probably due to the trace not being exactly 50 ohms, but it's pretty negligible. This kind of intuitively makes sense because if we have the trace open, no termination, then we get a fully positive reflection back. If it's shorted to ground, completely terminated, then we get a negative reflection back. And it makes sense that somewhere in between those, completely open or completely shorted, there would be somewhere where the fully positive and fully negative would cancel and you get 0. And that just happens to be what the impedance of the trace is, in this case, 50 ohms. And if I make the pulse a bit longer, you can see that it stays clean. We don't have any of that weird stair-stepping effect from the reflection hitting the end, coming back, and then going, back and forth. There are actually two ways we can deal with reflections. The first one that we just did is known as parallel termination. This is since our termination resistor connects to the transmission line in parallel. However, we also could have done series termination. With this method, we make sure that the impedance of whatever is driving the line matches the impedance of the line. This doesn't stop the reflection at the destination, but it stops the reflection after it comes back. So the reflection will go all the way to the end, reflect, come back and stop. This is actually exactly what we did when we had no termination at the end of the line. The signal generator has an output impedance of 50 ohms, so it sends the pulse, it goes back, or it reflects at the end, comes back to the signal generator, and then that's it. It absorbs the reflection. This demo board was originally designed for an FPGA to go on it and create the signals. However, as you notice, I've been using the signal generator so far to drive the lines. That's because an FPGA can't really drive a 50 ohm line with parallel termination. A 50 ohm load is just too much for a 3.3 volt signal. It would require 66 milliamps of current, and the FPGA pins max out at about 16 milliamps. This is the real advantage of series termination. By adding the resistor in line, when the line is in steady state, we don't need to provide any current to keep it high. The pins on an FPGA can easily handle the short pulse required to drive the line initially. After all, they have to do that every time they switch a signal anyways. If we were going to use an FPGA to drive a 50 ohm line, we would really have to use series termination. And to do that, we would need to find a resistor that would make the output impedance of the FPGA be 50 ohms. This wouldn't be a 50 ohm resistor, as the output of an FPGA has some intrinsic series resistance. So likely something like 30 ohms or 25 ohms. We could find what that needs to be by adding a resistor in series with the output of an FPGA and adjusting that value until we didn't see any reflections past that initial one. It's important to note that series termination only works for point-to-point signals. You can't look at the signal in the middle of the line and expect it to be clean. That's because in the middle you'll see both the signal you're sending and the reflections back. Let me remove the termination off this board and we'll sand some of the solder mask off and we can probe some intermediate signals. So I just went and sanded off some spots on the board here. Let me hook it all back up and we'll take a look. All right, I have everything set up again and we have a single pulse coming down the line. And just like before, since there's no termination, we can see the reflection coming back. Since the signal generator impedance is pretty close to our line, it's absorbing that reflection and we don't see another one bouncing back down the line. If we probe the end of our transmission line, just where it ends and there's no termination, you can see we get a nice clean single pulse just like we were sending with minimal junk coming back from reflections. However, if I then probe the middle of the line, or somewhere random in the middle, you can see we get not only the signal going, but we also get the reflection coming back, and it gives us this elongated kind of, ugly signal. If this was longer, we would get two individual pulses. If I probe closer to the end of the line, you can see we get closer to a nice, peak. And if I probe further down the line, or here we go really close to the beginning, we get closer, much closer to the two pulses. And then if I probe further down here, I gotta switch grounds because the cable's not that long. Now we're seeing, again, two individual pulses separated pretty significantly. While back at the receiving end, we get a single clean pulse, which is exactly what we want. So with series termination, we have the benefit that when the line is stable, not switching, we don't have to drive a full 50 ohm resistor. We only have to drive that initial load during the swing, during the upswing or the changing of the signal. The big downside is that you only get the clean signal at the very end of the line. Anywhere intermediate, and you end up with weird combinations of the pulse plus the reflection. With parallel termination, you don't get this because there is no reflection. The parallel termination absorbs all of that energy. The big downside is that you have to drive the line as if it's a 50 ohm line the entire time. So it takes a lot more current to do. What's perhaps a bit interesting is that if we look at the signal going down the line, like maybe here, we can see that these two pulses are only half the height of the received signal. And that's because the received signal is both the signal we're sending plus its reflection added together perfectly in sync. However, when we're somewhere else, those heights are no longer perfectly in sync because the reflection and the signal we're sending are out of phase. So we get a shorter pulse that are about half the height of the magnitude as what we would see at the end. I've been using 50 and 100 ohm impedances a lot as examples. This is because they are by far the two most common values you will see. When you have a single-ended signal, it's typically pretty easy to set the stack up and the geometry of the PCB to make 50 ohms easy to route. For differential signals, the same is true for 100 ohms. The reason differential signals are double the impedance of a single-ended signal is that you're driving both traces opposite each other. When you raise the voltage of one trace by 1 volt, the other one drops by a volt. So for a swing of 2 volts, you have about the same amount of current running through them. This makes it look like twice the impedance of either single trace. However, differential signals also couple to each other. The coupling increases their capacitance and lowers their inductance. This results in a lower overall impedance. Depending on how close the traces are, you may see that what would be two 50 single ohm traces would have something more like 90 ohms of impedance when used as a differential pair. The 90 comes from doubling 50 to 100, and then the coupling of the two traces subtracts a bit off them. A question I had when I was first learning all of this is that if we get a reflection every time there's an impedance mismatch, if we have to cause a mismatch, wouldn't it be better to stick with the new missed match impedance instead of going back to the original, causing another mismatch? So for example, if we had a 100 ohm differential signal and we needed it to go around something like a BGA pad, that would cause it to jump up to something like 120 ohms. Wouldn't it be better to just keep the trace at the new spacing, leaving it at 120 ohms, instead of bringing them back, causing it to have another mismatch going to 100 ohms? It turns out that no, this isn't better. If you have an impedance mismatch, you want it to be as short as possible. This is because the second mismatch will cause a reflection opposite of the original mismatch. These reflections will largely cancel out if the mismatch is really short. However, the longer the mismatch gets, the more delay there is between the original reflection and the inverted reflection, making them cancel less perfectly. I have some traces on this demo board with different mismatches. We're going to take a look at 5 differential 100 ohm pairs on this board. One of them is just a really long trace without any mismatches. 2 of them have major mismatches of about 50 ohms, and 2 of them have minor mismatches of about 75 ohms. Each intensity has one with a long mismatch and one with 3 shorter mismatches. We're going to take a look at the signal integrity of all of them. Here I have an Alchitry AU set up to send 10 nanosecond pulses through the 5 differential pairs using LVDS. For this demo, I've switched out the probe to this differential probe as we're looking at differential signals. This is just like a regular probe, but it takes the difference of the 2 signals instead of referencing one to ground. And I can start by probing our reference, which is the really long trace with no mismatches. And if I get this correct, put the minus in the minus, we can see we have a pretty clean signal here. The edges aren't super sharp, and that's because the trace is quite long. We see a nice rising edge and a falling edge, very clean, nothing unexpected. Now we can take a look at the mismatch that's the worst, where we have a long mismatch of 50 ohms. So the trace is normally 100, and the mismatch is somewhere around 50. Now when we look at the signal, you can see we have much sharper rise and fall times. That's just because this trace is much shorter, but we have a lot of junk, which is the reflections bouncing back and forth on the mismatch and back and forth through the line. The signal integrity of this is obviously pretty bad, and we're using 10 nanosecond pulses, which are fairly long. If you were running at like a gigahertz, the width of this pulse would only be a tenth of what it is here. This is the equivalent of like a 100 megahertz bus, and you can see how this could easily impact your not only the signal you're sending, but even multiple bits later. If we quickly cycle through the 4 of these with mismatches, I would say going from worst to best, it seems like the worst one is the bad mismatch that's very long, which is here. Then we have the not as bad mismatch that's long, and then the bad mismatch of 3 short bursts, and the 3 short bursts of the not as bad mismatch being the best one. This is not unexpected. The length of the mismatch matters more than the severity of the mismatch. Even if you have a really bad mismatch, if it's really short and your signals aren't traveling that fast, the opposite reflection will cancel the first reflection so that it isn't that bad of an issue on your signal. However, if you have a really long mismatch, then it has time for those reflections to get separated, and then they no longer cancel very well, making it much worse. And we can see that here with the short mismatches being substantially better than the single long mismatch. That's more or less what we would expect. The longer the mismatch, the worse it is. The worse the mismatch, the worse it is. So the rule of thumb to take away from this is when you have to have a mismatch, make it as small as you can and make it as minimal as you can. With that said, if your data speeds aren't that high, even with an insanely terrible mismatch, this would be a reasonably acceptable signal if you were only running at 100 megahertz. I hope this video gave you some insight into what the characteristic impedance of a transmission line means and how that affects signals propagating through it. If you found this video helpful, don't forget to like, comment, and subscribe. It really helps out the channel. And as always, thanks for watching.